Today we're going to talk about classes, one of the core building blocks of object-oriented programming, and we'll look at how classes are implemented and used in Python. You can think of a class as a blueprint or a template. Just like this star-shaped mold on the slide, a class defines the shape and structure of something, but it's not the thing itself. The actual objects we create, called instances, are like the finished soaps. They all share the same structure, but each instance can have its own data and behavior. By the end of today's lecture, you should be comfortable reading and writing simple classes in Python, creating objects from those classes, and understanding how data and behavior are bundled together. Before we go deeper into classes, we need to talk about methods, which are also commonly called functions. A method is simply a named sequence of instructions. Instead of writing the same steps over and over again, we package those steps into a single unit and give it a meaningful name. This idea of packaging is important. When we put multiple steps into a method, we make our code easier to understand, reuse, and maintain. Think about it this way. When you see a method call, you don't need to know every line inside it immediately. The name of the method tells you what it does and the details are hidden inside. A function group's behavior, it tells the computer how to do something. But real-world problems don't just have behavior. They also have data that needs to be stored, updated, and protected. That's where classes come in. A class groups data and behavior together. Instead of having data floating around in variables and behavior scattered across functions, a class keeps everything related in one place. For example, a student class might store a student's name, an ID, but its methods might calculate GPA, print a transcript, or update enrollment information. A student class isn't just a set of functions, and it's not just a collection of variables. A student has data, like name and ID, and behavior, like enrolling in a class or calculating GPA. When we create objects from a class, each object carries its own data and knows how to operate on that data using its methods. This approach scales much better as programs grow. When systems get large, managing dozens of global variables and standalone functions becomes difficult and error-prone. Objects help us manage complexity. They let us break a large system into smaller, self-contained pieces that are easier to understand, test, and maintain. That's why modern software, from games to mobile apps to large enterprise systems, is built around objects and classes. What you're looking at here is a blueprint of a starship. It shows structure, components, and how everything fits together. But this blueprint is not the ship itself. In programming terms, this blueprint is like a class. A class defines what something looks like and what it can do. It specifies the parts, data, and the operations, methods. But it doesn't actually exist in the real world yet. The real ship, the one flying through space, that's an object or an instance of the class. You can build multiple ships from the same blueprint. Each ship follows the same design, but each one is a separate object with its own state. This is exactly how classes work. A class defines the structure once, and then we can create many objects from it. Each object has the same methods, but its own data. One ship might be docked, another might be in warp. Same class, different state. This is why classes are so powerful. They let us model complex systems in a clean, organized way without rewriting code over and over again. As we move forward, keep this picture in mind. Class equals blueprint. Object equals the real thing built from that blueprint. Now let's formalize some of the key terms we've been using. At the center of object-oriented programming is the idea of a class. A class is a blueprint or a template. It describes what something is made of and what it can do, but it is not a real thing by itself. Inside a class, we define two main components. First are attributes. Attributes represent the data, the information we want to store. For example, a student's name, ID number, or GPA. Second are behaviors, which are implemented using methods. Behaviors describe the actions an object can perform, such as enrolling in a class or calculating a GPA. So when you look at a class definition, you should always be asking, what data does this object store and what behaviors does it support? Once we have a class, we can create an instance, which is also called an object. An instance is a real, concrete version of the class. It follows the blueprint, but it has its own specific data values. For example, you might have one student class but many student objects, each with a different name and ID, all using the same methods. This distinction is extremely important. The class defines the structure. The object is the actual thing you work with in your program. Next, we'll see how this looks in actual Python code. Now let's look at a very simple Python class example. On line 1, we define a class named sample. This is the blueprint. We're not creating an object yet. We're just defining what the class looks like. Inside the class, on line 2, we define a method called display. This method contains behavior. In this case, it simply prints a message. On line 3, the print statement is the actual work being done by the method. Then on line 5, we call sample.display. Notice something important here. We are calling the method directly from the class, not from an object. This works in Python because methods are essentially functions stored inside a class. At this point, we are focusing on structure, not yet on objects or instances. This example is intentionally simple so we can focus on how a class and a method are defined before we introduce more details. We'll improve this example by creating an instance of the class and by introducing the self parameter, which allows methods to work with object-specific data. Now let's look at a more realistic Python class example. On line 1, we again define a class named sample. This is still just the blueprint. On line 2, we see a special method called init_underbar. This is the constructor. The constructor runs automatically every time we create a new object from the class. Notice the first parameter, self. In Python, self refers to the current object being created. The second parameter, age, is a value passed in when we create the object. On line 3, we assign self.age equals age. This creates an instance variable named age that belongs to this specific object. Every object created from this class will have its own age value stored inside it. Next, on line 5, we define another method called display. Again, notice that self is the first parameter. This allows the method to access the object's data. On line 6, we print the value of self.age. This shows how a method can use an instance variable. On line 8, we create an object by calling sample25. This line does two things. It creates a new object, and it calls the constructor with age set to 25. Finally, on line 9, we call obj.display, which prints the age stored in that object. This is the core idea of object-oriented programming in Python. Data lives inside objects, and methods operate on that data. Let's lock in the basic syntax rules for writing classes in Python. First, class names use camel case. This is a convention, not a rule enforced by the language, but it's extremely important for readability and professionalism. Second, methods are defined inside the class using the def keyword. Indentation matters in Python. Everything that belongs to the class must be indented under the class definition. Third, and most importantly, self refers to the current object. Anytime you want to store data inside an object or access that data later, you must use self. In the code example at the bottom, notice the overall structure. We start with class name. This defines the blueprint. Inside the class, we define the constructor using init. This method runs automatically when an object is created. Inside the constructor, self.attribute equals value creates an instance variable that belongs to the object. Every object created from this class will have its own copy of that attribute. If you forget self, Python will not know whether you're referring to a local variable or an object's data, and your code will either fail or behave incorrectly. These rules may feel small, but they form the foundation of every object-oriented program you'll write in Python. Let's look at an example. Here, we define a student class. The constructor takes a name and a student ID, and it also initializes credits to 0. Every time we create a student object, the init method runs and sets up that object's data. On line 7, we create our first object, S1, and send in Alice and V 0010000. On line 8, we create a second object, S2, and send in Bob and V001000101. Even though both objects come from the same class, they are completely separate objects in memory. Each object has its own copy of the attributes. S1 has its own name, ID, and credits, and S2 has its own name, ID, and credits. When we print S1.name, we get Alice. When we print S2.student_ID, we get Bob's ID. This is the key idea. A class defines the structure, but each object stores its own data. You can think of the class as a form, and each object as a filled-out copy of that form. We're still using the same student class, but this time we added one more method, add credits. Notice that, like the constructor, add credits has self as its first parameter. This tells Python that the method belongs to an object and that it can access and modify that object's data. Inside add credits, we update self.credits by adding the given amount. This is important. The method is not changing a global variable. It's changing the state of one specific object. On line 10, we create a student object named S1. On line 11, we call S1.addCredits3. When this method runs, only S1.credits is updated. Finally, when we print S1.credits, we see the updated value, 3. Now let's look at a very common mistake when writing classes in Python. At first glance, this code might look reasonable. We define a counter class, and inside the constructor, we set count equals 0. But this code is wrong. The problem is that count is just a local variable inside the init method. As soon as the constructor finishes running, the variable count disappears. That means the object does not actually have a count attribute. On line 7, we create an object using obj equals counter. At this point, the constructor runs, but it does not attach count to the object. Then on line 8, we try to access obj.count. Python now looks inside the object for an attribute named count. It doesn't find one. So Python raises an attribute error, meaning this object does not have an attribute called count. This error is one of the most common errors you'll see when working with classes in Python. The key lesson here is very simple but very important. If you want a variable to belong to an object, you must use self.variableName. Without self, the variable lives only inside the method and disappears when the method ends. In the next slide, we'll fix this class by correctly defining self.count, and the error will go away. This version of the counter class is written correctly. On line 2, we define the constructor init just like before. But on line 3, notice the key difference. We use self.count equals 0. This attaches the variable count directly to the object. Now count is an instance variable, and it belongs to every counter object we create. On line 5, we create an object using obj equals counter. When the constructor runs, self.count is created and initialized to 0. On line 6, when we print obj.count, Python finds the attribute and prints the value. This time there is no error, and the output is 0. The only change between the wrong version and the correct version is the use of self, but that one change makes all the difference. Whenever you see an attribute error in Python, one of the first things you should check is whether you forgot to use self when defining an instance variable. Now let's talk about an important distinction in object-oriented programming: instance attributes versus class attributes. First, an instance attribute belongs to one specific object. When we create an instance attribute using self.variableName, that variable is stored inside that particular object. If we have two objects, each object gets its own copy of the instance attribute, and changing one does not affect the other. Second, a class attribute belongs to the class itself, not to any single object. That means a class attribute is shared by all objects created from that class. Every object can access it, and if it changes, the change is visible to all objects. This difference is extremely important because using the wrong type of attribute can lead to subtle bugs. A good rule of thumb is this: if the data describes an individual object, it should be an instance attribute. If the data describes something common to all objects, it should be a class attribute. Here we define a class called bank account. On line 2, notice the variable interest rate equals 0.02. This variable is defined outside of the constructor and inside the class. That makes interest rate a class attribute. There is exactly one interest rate, and it is shared by all bank account objects. Next, in the constructor, we define owner and balance using self. These are instance attributes. Each account has its own owner and balance. So if we create two bank accounts, they may have different owners and balances, but they will both use the same interest rate. This makes sense conceptually. The interest rate is a property of the bank, not of an individual account. If the bank changes the interest rate, that change should apply to all accounts. This slide shows one of the most dangerous and subtle bugs you can write in Python classes. At first glance, this class looks fine. We define a class called bad, and we create a list called items. The problem is where that list is defined. Items is a class attribute, not an instance attribute. That means there is only one list, and it is shared by all objects created from this class. Now watch what happens. We create obj1 with the value 1, and then we create obj2 with the value 2. Both constructors append their values to the same list. So when we call obj1.printItems and obj2.printItems, they both print the exact same contents. This is almost never what you want, and it leads to bugs that are very hard to track down. To recap, a class is a programmer-defined data type. It allows us to group related variables which store data and methods which define behavior. In other words, a class combines data and the operations that work on that data into a single unit. This organization makes programs easier to understand, manage, and maintain. A method is a named list of statements. When we refer to a method by its name, those statements are executed. A method may also return a value back to the caller. Calling a method is referred to as a method call. Any value we pass into a method is called an argument. Methods allow us to organize code, reuse logic, and define behavior. There are two different ways we can use classes in Python. First, we can create an instance of a class and use it. In this example, we define a class called dog, and then we create an object called myDog from that class. Once the object is created, we can call its method by calling the myDog.bark method. This is the most common way we work with classes, by creating objects and using their behavior. The key idea here is that each object is an instance of the class and can perform the actions defined in that class. So remember, we define a class as a blueprint, create objects from it, and then use those objects to run methods. The second way we can use classes in Python is by using class-level functionality directly. In Python, this is usually done through built-in modules or class methods, where we don't need to create an object first. For example, when we write math.square-root-5, we are directly using a function provided by the math module. We didn't create a math object. Python allows us to access that functionality directly. So the key idea here is, sometimes we don't need an instance. We can directly use functionality that belongs to a class or module. This is similar to what Java calls static methods, But in Python, we often see this pattern with modules or special class methods. Here is an example written in Python. We define a class called callee. Inside the class, we define a method called printMyName. Notice that in Python, every instance method must include self as the first parameter. This represents the current object. So this method will print the name June when it is called. Now let's look at how classes are used across multiple files in Python. In callee.py, we define a class called callee with a method printMyName. In caller.py, we import that class using from callee import callee with capital C. Then we create an object, obj, and call its method. This is important because in real programs, we don't write everything in one file. We organize code into modules and then import and use them where needed. So this demonstrates how classes help us structure larger programs across multiple files. Let's take a look at how import works. This line allows us to use code that is defined in another file. First, callee refers to the name of the Python file, callee.py. So Python looks for a file with that name. Then, callee with capital C is the class we defined inside that file. So what this statement is saying is, go to the file callee.py, find the class callee, and make it available in this file. Once we import it, we can use callee class just like it was written here. This is important because it allows us to organize our programs into multiple files instead of putting everything in one place. Before we wrap up, I want to emphasize something important. This lecture covers the most essential concepts related to classes, objects, and methods. However, it is not comprehensive. To fully understand classes and objects, you must read the chapter on classes in the textbook. The lecture is meant to guide you and highlight key ideas, but the textbook provides the full details, examples, and edge cases.
This lecture was prepared by June Lee with the assistance of AI Technologies. See you next time!